In this video, I will explain you the process of doping. First, I will explain you why doping is required. In the last video, we have learned what is intrinsic semiconductor. That is nothing but semiconductor made with only one element in it. So here, in the element of semiconductor, in the crystal of semiconductor, we can only see atoms which is silicon. Okay, only silicon atoms are present. Now, if we are replacing any of the silicon atom or number of silicon atom with an impurity added, then that is called as extrinsic semiconductor. Now, in this process, we are adding an impurity. What is impurity? Any element other than silicon. So, we are replacing a silicon from here and a new element is added. Now, it cannot be any impurity. These impurities has got certain features. So, I will first explain doping is mixing of a semiconductor with choice impurity. This one is very important. So, impurity that has got special properties in a measured quantity. It's not a random mixture. Certain elements are taken, that elements have certain property and these are mixed with pure semiconductor to get an extrinsic semiconductor. So, the process of adding an impurity is called as doping. What is impurity? Any element other than silicon. So, here I am going to choose two types of impurity. One is pentavalent impurity, and next one is trivalent impurity. What is pentavalent impurity? As the name suggests, that has got valency 5. What is trivalent? Tri stands for 3, so that has got valency 3. Now what will happen when I am adding pentavalent impurity? Example for pentavalent impurities are phosphorus and arsenic, and there are many. Okay, and trivalent impurity, the important one are aluminum and boron. Now, say for example, I am going to add a impurity which is phosphorus to a silicon crystal. What will happen? Phosphorus has got 5 valency. So, when we are replacing phosphorus with silicon, it will have 5 electron to share with nearby silicon atom, and in addition to this it will have 1 electron. Because phosphorus is having 5 electron in its valence orbit, or 5 is the valency. Now phosphorus gives 4 electron to share with nearby 4 silicon atom. Now anyway, this has got stability, this has got 8 electron in the outermost orbit and there are no holes generated. But what we can see here, we have an excess electron. And these electrons now can contribute towards conduction because these are free electron. So this is process of converting an intrinsic semiconductor into an extrinsic semiconductor by adding an impurity which is pentavalent in nature. Now we have one more process, one more type of extrinsic semiconductor which is nothing but made on adding trivalent impurity. For example, aluminum and boron. So when I am keeping an aluminum here, aluminum has got only 3 valency. So 1 it will contribute, 1 more it will contribute, 1 more it will contribute, and to share with this silicon it will not have any electron. See, 3 dotted points are representing the electrons that aluminum owns, and it shares it with nearby silicon atoms, and these silicon atoms are also contributing its one of the valence electron to make a covalent bond. But see, here covalent bond is made, here it is made, here it is made, here it is made, but aluminum is not able to contribute anything. So these are called, so here there is a vacancy and these vacancy are called as holes. Okay, now this have a tendency to attract electrons nearby. what will happen if it is attracting? That electron will take this seed and this will become a hole. Now this can take an electron from here. This will become a hole and this will now be occupied by electron which is contributed by this silicon. Okay. So I hope this concept is clear. Concept is very simple. Doping is nothing but process of adding impurity. Now what is impurity? See, these are choice impurity that has got special property. And what are these properties? One type of impurity has got pentavalency or valency 5, and next type of impurity has got trivalency or valency 3. Now when we are adding, these are called as dopant. Okay, this impurity can also be called as dopant. So when we are adding a dopant of pentavalency, an excess electron is generated and that will contribute towards conduction. And when we are adding a dopant of trivalency, then a hole is generated, an excess hole is generated, and this hole can contribute towards conduction. Now I have a tricky question with you. What would be the net charge of an extrinsic semiconductor which is added with pentavalent impurity? You may say that with pentavalence, by doping by pentavalent impurity, it will get excess electron and that would be negatively charged. No. See, now just assume a crystal which is fully made by silicon. So all silicon atom has got 4 valence electron and these are shared with nearby 4 electrons. Now it is having 8 electron anyway in the outermost orbit on sharing with other silicon atom. Okay, now I can say that these silicon atoms are neutral because there are no excess electron, no excess holes. But when I am removing a silicon atom from here, then I am taking a neutral silicon atom. All silicon atoms which contribute towards the crystal formations are neutral and the whole crystal is neutral. I am saying intrinsic silicon crystal is neutral, which is a crystal which is made up of only silicon atom, that is neutral. From there I am taking one silicon. So from neutral I have removed one silicon and I am adding an aluminum atom. Now aluminum is basically neutral and I am adding a neutral element. Once again I will repeat. See, the crystal was neutral. From this I have taken a silicon atom which is neutral and I am adding an aluminum atom which is again neutral. But as aluminum is having an excess electron, excess from 4 valency, so it has got 5 valency. So when we are comparing with silicon, it is having 1 excess electron, but that doesn't mean that it has got negatively charged. Now when there are excess electron inside aluminum nucleus, there is 1 excess proton. Is that clear? In aluminum, I am adding an impurity. Now that impurity has more proton in it, equal to the number of electron it is having in the orbits. So anyway, I could say that it has got an excess electron. Now this electron would contribute towards conduction, but the net charge of an extrinsic semiconductor is 0, though it is having excess electron. Is that clear with you? It's a very important point. You can just assume that from a neutral element, I have taken one neutral element and I have added one a different neutral element. So all in the whole transaction, only neutral scenarios, neutral steps are made. Okay, in each step only neutral conditions are accomplished. Okay, now this goes same with adding trivalent impurity. In that case, an excess hole is made, but the whole semiconductor crystal, that extrinsic semiconductor crystal, is neutral. Now intrinsic semiconductor, which is neutral, and extrinsic, 2 types are there, adding with pentavalent impurity and adding with trivalent impurity. These are called as N-type semiconductor, these are called as P-type semiconductor. I will explain in detail in the next video. But anyway, here also the net charge of the semiconductor crystal, whether it is added by pentavalent impurity or trivalent impurity, that would be 0. But in intrinsic semiconductor, whatever the number of electrons free electrons we are having, equal to that we will have number of holes. So number of electrons would be equal to number of holes. Number of free electrons is equal to number of holes. Because in intrinsic semiconductor, whenever one electron is generated, excess electron is generated, at the same moment one hole is generated. It's not excess electron whenever a free electron is generated. So from a silicon, let's say there is no aluminum, it's all silicon. Let's say one electron move from this position and become free. So this is a free electron, this is a hole. So one electron hole pair is generated. At the same time, if one electron is, if it go away from this particular valence bonding, if it is coming out, then this would be hole, this would be a free electron. Again, one more electron hole pair generated. If that happen here, electron go out, a hole is generated. So always electron hole pairs will be generated in intrinsic semiconductor, so that I could say number of electrons are equal to number of holes. But in the case of extrinsic semiconductor, that is not the scenario. If I am adding an element of pentavalency, one excess electron would be contributed, would be given to the crystal, and where we have more number of electrons as compared to holes. Now in the case of adding with trivalent impurity, only 3 electrons are there. So one hole is there in excess to the all other electron hole pairs. Okay. So in trivalent impurity, in a semiconductor added with pentavalent impurity, one excess electron would be there. No, not one excess. Whatever the number of whatever the number of impurity it is having, equal to the number of impurity, it will have excess electron. So if 2 aluminiums are added in the whole crystal, then 2 excess electron would be there. Okay. Now in the same, it would go same with trivalent impurity, but the difference is, if it is having 3 aluminum added, then each aluminum will lack by 1 electron, which means each aluminum will have 1 hole. So this is aluminum. So when 1 aluminum is added, 1 hole is there, 1 excess hole. If 1 more aluminum is there, 1 more excess hole is there. If 1 more aluminum is there, then 1 more excess hole would be there. Okay. And these semiconductor crystal, which are extrinsic semiconductor, will also be having electron hole pair generation, because see, that will go normally with the temperature. That is, in a purest silicon semiconductor, when we are heating, electron hole pair would be generated. Okay. Now in extrinsic semiconductor it would be there, and also in intrinsic semiconductor it would be there. But in extrinsic semiconductor, which are nothing but added with impurity, always there would be 1 excess electron if it is N-type semiconductor, that is nothing but doped with pentavalent impurity. Now at the same time, in P-type semiconductor, that is doped with trivalent impurity, it will have 1 excess hole. So if you are calculating the total number of holes as, for example, 5, and if total number of free electrons as 4, which means that is a semiconductor added with trivalent impurity. See, 5 is the number of holes and 4 is the number of electron. Now I can equate this as 4 electron and 4 holes and 1 excess hole. Now 4 electrons and 4 holes are generated thermally in the crystal, and the additional hole it has is due to presence of 1 impurity, which is aluminum or boron, whatever it is, but anyway it's a trivalent impurity, and that trivalent impurity has given an additional hole in that crystal. If the question is, if one semiconductor is having 7 electron and 6 hole, what type of 7 free electron and 6 number of holes, what type of semiconductor it is? See, 7 electron and 6 holes can be written as 6 electron and 6 holes. See, these are electron hole pair, these are thermally generated in the semiconductor crystal, but the 1 excess electron it has came from doping of a pentavalent impurity, that is either phosphorus or arsenic, but anyway it's a pentavalent impurity. That is the reason for the excess electron. If that concept is clear, then this chapter would be very fine with you. Okay, so this one is, in short, extrinsic semiconductors are nothing but semiconductors doped with an impurity, and the impurity are nothing but a choiced impurity. So which are the choices? Pentavalent, element that has got pentavalency or trivalency, and these are added in measured quantity. Okay, that's all. Thank you.